Welcome to this explainer. Today, we're bridging the gap between invisible molecular structures and the everyday plastic products we all rely on. We're going to master the foundational science of injection molding, because truly understanding the properties, the components, and the applications of these common plastics, well, that's exactly what separates good design from truly great manufacturing. Let's get into it.
Here's our roadmap for unpacking these materials today. First, plastic types in molding. Second, amorphous versus semicrystalline structures. Third, thermal properties and shrinkage. Fourth, common injection molding materials. And finally, number 5, real-world applications.
All right, jumping right into part 1, plastic types in molding. Let's start broad and look at the highest level classifications before we get too granular.
So, the materials we mostly used in this field are called thermoplastics. As the definition highlights, they are fundamentally defined by their ability to melt when heated and then solidify when cooled. This phase-changing behavior is the absolute core of the injection molding cycle. It allows for repeatable processing. You can take pellets of thermoplastic, melt them down in the barrel of a machine, inject them into a mold, and cool them right into a solid part.
Now, it's totally crucial to contrast those thermoplastics with another category you'll definitely encounter, thermosets. Unlike thermoplastics, which you can melt and remelt over and over, thermosets undergo a permanent chemical cross-linking process when they're heated and formed. Think of it like baking a cake. Once it's baked, you can't exactly melt it back into batter, right? Materials like phenol formaldehyde fall into this bucket. Because they permanently cure, they can't be remelted, and that makes them perfect for entirely different extreme applications, like high-heat engine components or distributor caps, where you absolutely do not want your plastic melting.
Moving on to Section 2, amorphous versus semicrystalline molecular structures. We know thermoplastics melt, but what are the molecules actually doing on a microscopic level?
Well, there are two main classes here. First, we have amorphous polymers, which basically look like random tangled bowls of molecular spaghetti. Their structure doesn't follow any strict pattern. But then we have semicrystalline polymers. When they're heated, sure, they untangle, but as they cool, they fold back into these highly ordered, tightly packed crystalline structures. This fundamental difference in molecular reorganization is the secret behind why different plastics behave so incredibly differently inside a mold.
So the crucial takeaway here is that this crystallinity isn't just some fun chemistry trivia. It literally dictates the physical reality of your manufactured part. For semicrystalline materials, the rate at which that molten polymer cools directly affects how those ordered regions form. If you cool the plastic slowly in the mold, the molecules get more time to fold and pack tightly, which means more crystalline regions form. And that degree of crystallinity directly influences the dimensional quality, the strength, and the shrinkage of your final part. Basically, you have to control the cooling if you want to control the plastic.
Which brings us to Section 3, thermal properties and shrinkage. So, how do these microscopic structural differences actually translate into physical changes on the factory floor?
What's really fascinating about shrinkage is the massive contrast between our two polymer types. With an amorphous material, the specific volume, which is essentially how much space a specific mass of the plastic takes up, drops pretty steadily as the temperature decreases. But with a semicrystalline material, there's a much sharper, way more dramatic drop in volume as it cools and forms those dense folded structures. Also, if you apply higher pressure during the packing phase of molding, you can actually shift these thermal curves. This allows engineers to compensate for that volume loss as the material solidifies.
Understanding these specific volume changes is how engineers predict and account for shrinkage. Ideally, what we want is isotropic shrinkage. That means the shrinkage occurs equally in all directions as the molten plastic cools inside the mold. By knowing exactly how much a specific polymer is going to shrink based on its thermal properties, a mold designer can cut the steel of the mold just a tiny bit larger than the final product needs to be. That ensures that as the part cools down, it shrinks uniformly into the exact perfect dimensions.
All right, Section 4, common injection molding materials. With all that molecular theory locked in, let's explore the actual materials you'll encounter out in the wild, their specific components, and their unique properties.
Taking a look at some data pulled directly from mold flow laboratory environments, you can see distinct differences in mechanical properties between standard polymers. Take polyamide, or PA, which is a semicrystalline polymer. It has a massive elastic modulus, meaning it's incredibly stiff, and it's highly dense at over 1,500 kilograms per cubic meter. Compare that to polypropylene, or PP. It's also semicrystalline, but its modulus is much lower, and it's significantly lighter. Meanwhile, the amorphous polymers like ABS and polycarbonate sit somewhere in the middle when it comes to stiffness, but polycarbonate is noticeably denser than ABS. And it's not just the final properties that differ. These materials require vastly different processing setups just to mold them in the first place. For instance, polyamide requires scorching melt temperatures up to 350 degrees Celsius just to flow properly. Contrast that with polypropylene, which can process at a much cooler 190 degrees. Even the mold itself has to be heated differently. A mold for polyamide might run at 160 degrees, while a polypropylene mold can run at pretty much room temperature. So choosing the right plastic literally dictates your entire manufacturing setup.
Beyond those 4 core thermoplastics, we have some incredibly versatile variations. Take PVC, for example. Unplasticized PVC is rigid and strong, making it perfect for industrial pipe fittings. But if you add plasticizers to it, it becomes flexible enough for things like shoe soles and toys. Then there are polyurethanes, which are known for rapid curing and high impact strength. They're heavily utilized in TV and computer housings. And hey, let's not forget our thermoset friend, phenol formaldehyde. It boasts high strength and a really low tendency to deform under stress, which makes it ideal for heavy-duty mechanical components like pulleys.
Finally, Section 5, Real-World Applications. Let's ground all this science in reality and see exactly how these thermal properties dictate commercial design choices.
Consider a mass-produced item like a small cosmetic compact. It might look super simple at first glance, but structurally, it's actually quite demanding. It requires precise sliding hinges to open and close smoothly, rib supports for rigidity, and a very specific locking snap fit mechanism, that little tiny bump you press to click it shut, to function perfectly over thousands and thousands of uses.
Now, you can't mold a complex part like that out of just anything. A compact base like this is typically molded from a blend of ABS and sand polymers. Why? Well, because, as we learned earlier, ABS is an amorphous polymer. And that amorphous nature provides the incredible dimensional stability and uniform shrinkage required for those tiny, precise mechanical features. It offers good heat resistance, high heat deflection, and the exact ideal balance of hardness and toughness. That means the snap fit isn't going to break off, and the thin hinge areas will maintain their rigid structure without cracking under everyday stress. The material choice perfectly matches the product's functional requirements.
And this whole concept applies to larger-scale geometries, too. Think about deep draw shapes, like a 100mm deep cup. Whether you're molding a tiny cosmetic snap fit or deep cavities like that, truly understanding the specific polymer's viscosity and its unique cooling behavior is the absolute only way to prevent warpage. If you tried to mold a deep cup out of a highly crystalline material without controlling the mold temperature perfectly, the differential shrinkage would warp those straight walls right out of tolerance in a heartbeat.
It's pretty wild when you think about it. Every single plastic product you interact with is a little masterpiece of material science. So the next time you hold a plastic product, ask yourself, what invisible molecular behaviors, what crystalline folds, and what precise thermal decisions made this exact design possible? Because mastering these properties and applications, that unlocks the ability to build almost anything. Thank you for joining me on this explainer, and keep questioning the science behind the everyday objects around you.